Welcome. In this video I'm going to show you how you can perform a post-hoc and residual analysis after a goodness of fit test using binary test or a residual test and Excel. I have a separate video where I show how to do this with my stikpet e add-in, which actually would boil down to simply using a function, but in this video I won't be using those. These residual goodness of fit tests are one way of doing a post-hoc analysis. They will actually compare the observed count of each category with the expected count. Alternatively, you could do a pairwise pairwise analysis, where you compare every possible combination of two categories. I have separate videos on those. And besides using a binomial or residual test, we could also use a goodness of fit test again. So again, a separate video on that. Now the residuals test, first of all, I have my data as an example in column A, and the first thing I do is I get the counts for each category. So that's a simple count if. You might notice my Excel is using a semicolon to separate parameters. Yours might be using a comma. I copy paste that down, and also the sum is in here. The number of categories is simply 5. I could do a count on the frequencies, for example. Then in this case I've entered my expected counts, but if you don't have any and just want to assume every category equal, you could just do the total divided by the number of categories. But here I'm just specifying a few different expected counts. The sum, of course, is actually again equal to the sum of the original observed counts. Now the standardized residuals are the observed counts minus the expected count divided by the square root of the expected count. So that's what I'm doing here. I'm taking the observed minus the expected divided by square root of the expected. You can also have adjusted standardized residuals, which is slightly different. Again, observed minus expected, but then the square root of the expected times 1 minus, and then actually the proportion of expected counts. So that's the expected counts divided by the total. And that's exactly what this formula is doing. Now these are z values, so we could use a standard normal distribution to calculate the corresponding p-values. So 2 times and then 1 minus the absolute value of the z value, and we want it to be cumulative. We could then actually have these for multiple testing. We might want to say, well, we're just going to use a Bonferroni correction. I have separate videos on how to calculate different types of adjustments for this, but Bonferroni is the most straightforward. It just says to multiply this with the number of comparisons, unless that becomes bigger than 1, because then it should just be 1. So that's exactly what's being done in here. Now if this is below 0.05, or at least that's the usual threshold, we would say we have a significant difference with the expected count. So that's for married the case, not for divorced, not for separated, for never married yes, and for widowed no. If you want to perform one of these binary tests, then the beginning is fairly the same. We do again a count if, we do again the categories. Now we have the expected counts again, but now I also actually calculate the expected proportion, which is just the value divided by the total. These dollar signs, you can actually toggle them with F4. Make sure that if I copy paste this down, this cell reference doesn't change. If you want to do a proportion test, so the score or the volt, these are the formulas. I have separate videos on these, so you can watch those if you're really interested in it, but it's a matter of filling out the formula. The observed minus the expected divided by the square root of the expected times 1 minus the observed proportion. And for volt, it's actually the same, but then instead of here having the expected proportions, we actually have the observed proportion, and the same over here. So in the denominator, it's all about observed in volt, and it's all about expected in score. These are z values, so we can use a normal distribution, and we can calculate 2 times, and then because we want it two-tailed, the 1 minus, and then the absolute value of the z value cumulative set to true. We adjust them again with Bonferroni, similar as before, but we take the minimum of 1 and the p-value multiplied with the number of tests that we're actually doing. A binomial test is a little bit trickier to do, so again I have a separate video on one sample binomial test, but I have the observed counts, the expected counts, the proportion of those observed counts, the proportion of the expected count, and then what I do is I do a binomial distribution with the observed count, and then as number of trials is going to be the E12, which is actually simply the, where is it, over here, the total sample size. And then we have the probability of success, which is the expected proportion, and cumulative set to true. We also have the other tail. If we simply, if it's greater than the observed count, then we do 1 minus, and then we also subtract 1 here. And then the significance of the two-tailed is the minimum of these two. Alright, so we do that for all of them. And then for the other tail, there are different ways of doing that. So here I'm just looking at the difference between the observed count, the expected count and the observed count. Then we actually do the equal distance method, so we do it in the other direction, and then we do the significance of the other tail like this. Once we have those, we simply add the two together, the one tail and the other tail. Then we can adjust for that by multiplying it again with the number of tests that we're actually performing. You could also use the method of small p. I have all the formulas in here, but I don't want to make this video too long. I'll leave a link on my website to this file so you can download it and study it a little bit. Or you can watch my one sample binomial test video where I'll also explain this. Alright, I hope this was still somewhat helpful, and thank you for watching.